Hi everyone, thanks for coming for this presentation about reconfiguration of spanning trees with degree or diameter constraints. So this talk is about reconfiguration. So what is a reconfiguration problem? So you are given two solutions of an instance of a problem and an elementary transformation between two solutions, and the goal is to determine if, given my current position, it is possible to reach the target one. So typical reconfigurations are, for instance, the Rubik's Cube, where you are given a Rubik's Cube where the colors are shuffled on the faces, and your goal is to reach this beautiful configuration where all the faces are monochromatic. But there are many other motivations, and not only combinatorial puzzles for reconfiguration, such that the study of Markov chain, some application to statistical physics or biology, for instance. So what are the main questions we are looking at in reconfiguration? So we are looking at the reachability problem where we are given two configurations and we want to determine if it's possible to transform the first into the second. So that's the case for the Rubik's Cube. We can look at the connectivity problem where, given any pair of configurations, we want to determine if it's possible to transform the first into the second. So that's, for instance, important in Markov chains because we want to determine if it's possible to reach any possible solution using our Markov chain. And there is also the minimization question where, given two configurations, we want to find the length of a shortest sequence. This is important, for instance, in applications to biology. And of course, all these questions have their algorithmic counterparts where we want to solve efficiently this problem in polynomial time or FPT time, for instance, or want to prove some hardness on the problem to show that such algorithms do not exist. So in this paper, we focus on spanning tree reconfiguration. So what is a spanning tree? A spanning tree is just a subset of edges that induce spanning subgraph without cycle. Okay, and what are the elementary transformation we are looking at? It's an edge flip. And what is an edge flip? We have the right to remove an edge, for instance, here the vertical edge, to move it anywhere else in the graph to another edge. Okay, and so one can ask, okay, given two spanning trees, is it possible to transform the first into the second by a sequence of edge flip? And the answer is, of course, yes, because spanning trees are matroids, and in a matroid, you know that you can always transform a solution into another in the optimal number of steps. And so in this paper, we are looking at the following problem where we are looking at spanning trees, but we add some additional constraints on the spanning trees of the intermediate transformation, like constraints on the maximum degree of the intermediate spanning trees or the diameter. So if you want to know more, please come to my presentation.